back into it. For the rest of class today, I'm going to give more examples about cost functions. There are two main, properties of cost functions and the questions that involve them that I want to go through this class by example. Complication one. The loop counter doesn't always increment by ones. Like say, I don't know, maybe you have a program and for some reason you have a list and only want to process even numbered values. Maybe you're trying to show that every even number is the sum of two primes or something through a program. I don't know. In order to analyze this using summation notation, you'll have to find a way to express the way that loop works without, while still incrementing only by ones. In this example, we have a while loop while k is less than n, and k increments by 2 every time. So how the heck would you do that? I think I'm just going to read out the solutions today since we have a lot less time than usual. The gist of this is that we're going to introduce a new looping variable that may not have the same values as the original k from the algorithm, but still involves the same number of iterations in that summation as there were in the for loop. So lines 1 and 2 have one step each. We're good. We notice that k counts up by 2, which means that it's always even. And since n is also even, we know that the values of k that'll actually be involved in the loop are the even numbers. And since the loop was bounded by n minus 1 in the original, and n is even, the largest even number that the loop will consider is n minus 2. So similarly to how we would define reindexed looping variables as like j equals k minus 1 or something, we're going to do the same idea just with division. We let j equal to k over 2. That way, we have a looping variable that works in a more familiar way, starts at 0 and counts up by 1s. And then from there, we can just count steps like usual. I should note again that the actual values of j don't matter here. All that matters is that the summation has as many terms as the original for loop had iterations. After the last iteration, we have k equals n. We check the loop condition once more, and then we get our final number of steps. Let's see, is this, just looking over the summation right now to see if it's interesting, and looks like it isn't. Just uses the identity for summation with a constant that you're familiar with. I think the rest of this slide is familiar. We already know, but it's worth restating, that on the final check of the loop condition, we count that as another step. And also that first point, it's okay if you didn't do this on the quiz, but I will expect you to do this on assignments. In your formal solution, you should justify your observations by referring to specific lines of code. That just means saying stuff like, wasn't there a line in the proof that said like lines 1 and 2 contribute one step each or something? you would say something like that. Aha. You would say stuff like line 1. You can do this on your own if you want. As a little hint, the analysis would be very similar, but it would involve the definition of odd numbers that we had talked about on the very first class and hopefully remember from Math 1240. This one's the really important one. If a piece of code has nested loops, you have to start the analysis from the innermost loop and work outward. Oh, I guess this has some annotations from when I was reviewing this on my own, so we get some for free. Neato. As you can see, most of these lines contribute 1 step each, but the while loops each contribute a summation's worth of steps to the final count. This one uses j as the iteration variable, counting up to k, but notice that the value of k will be different every time we reach this loop. Indeed, the value of k will differ by 1 each iteration of this while loop. So we won't be able to get a fully satisfying expression for the number of steps taken by the inner loop, but we can still set it up so that it contains no summation notation. And then when we analyze the outer loop, we'll have an expression that's defined in terms of k that we can then simplify and use our identities on. So first, we consider the inner loop. Like I mentioned, we don't know the value of k and we can't even say that it's defined in the program somewhere. We have absolutely no guarantees about what the value of k is when we reach this loop. Hence, we just let k be arbitrary. And then we analyze it as if we had a program-defined value of k, and as if this while loop was on, say, the first level of indentation. Luckily, we're counting up by 1s again, and each of the lines within the loop contributes 1 step, and then we get a total of 3k iterations. And then we have sort of an updated view of the algorithm that you probably want to copy when you're working on questions like these yourself. We sort of collapse lines 5 to 7 into a single line and say that that line contributes 3k plus 1 steps. Oh yeah, we have a plus 1 because of the loop condition being checked once more, as usual. With that out of the way, we can consider the outer loop. Again, we're just going up by 1s, so we don't need to worry about the complication from the previous example. Then we say the number of steps in one iteration is line containing only primitive operations, plus line containing only primitive operations, plus line that contains a loop, plus a line containing only primitive operations. We do some grade school addition to figure out that the number of steps in each iteration is 3k plus 4. And then count the total number of steps from all iterations by doing a summation over that number of steps per iteration. This algebra is mostly pretty straightforward, but there is one gotcha that I want to point out. So at first, we just use the fact that summation distributes to separate this from summation of 3k plus 4 into 3 times summation of k plus 4 times summation of 1. I guess I skipped a step in the explanation there. We're using the fact that summation distributes and the fact that you can factor out a constant in the summation. This constant summation uses the straightforward identity for constants to get n, which we multiply by 4 to get 4n. But this one, you may notice that we don't start from 1 and make it n. We start from 0 and make it to n minus 1. So your first instinct may be the same as my first instinct, and you might want to re-index that sum. Turn it into something like 3 times the summation from j equals 1 to n of j minus 1, j plus 1. Some sign. I'm going to get at worst and off by 1 error. But there's actually an identity that the slides don't explicitly point out. And you can sort of derive it from here, but I'm going to write it down anyway. Sorry, this has nothing to do with the number 3. Cool. The identity given in the slides, I believe, was summation from k equals 1 to n is n times n plus 1 over 2. As usual, I might be having off by 1 error. So I found this pretty neat. You could probably create other identities for summations starting from any number, going up to n plus or minus some offset. But I think you're good just knowing identities for the loop variables starting at 0 and starting from 1, because those are the two most common cases in code. Excuse me. So after the last iteration, we check the loop condition once more. It evaluates to false. And we get one more step, and then we have the total number of steps. From lines 3 to 8, that is. We also need to consider those boring one-step lines from the beginning of the program. And then we get our total cost. Just going to zoom out for a moment. Remember that what we're looking at here in general is that a algorithm or method or function you probably shouldn't call them functions, because that might be confusing with mathematical functions, but you can if you want. This method or whatever gets an input of size n. You could think of it, or one easy example is a list with n elements. And then our cost function expresses how many steps that the method will take. This gives you a measure of how fast the algorithm is that is much more reliable than testing it on any given computer or any set of different computers any number of times, because it abstracts away details like how many cores your processor has, how many, or what operating system you're running, what apps are running in the background. It's just math, and that's nice. Yeah, this totally has doodles from me looking through these on my own. I guess that works with the dramatically shorter class. I get these for free. This is another looping example with nested loops. All of these lines that don't have a little summation next to them are the ones that take just one step. This outer loop is a summation of something. We can't really tell because the inner loop hasn't been analyzed yet. And as such, we analyze the inner loop first and get an expression for how many steps it takes, and then use that finally to analyze the outer loop. And of course, this generalizes to any number of loops. You could have a loop with, or you could have an algorithm that goes like while, and you would do the exact same technique. Yeah, this is just the summation by constants identity that we saw earlier. I'd rather talk through the formal proof because it's presented way nicer. So we consider the inner loop first. This phrasing, let j greater than 0 be fixed, is essentially the same as saying let j be arbitrary, or let j greater than or equal to 0 be arbitrary. In both cases, we're saying that the variable definitely has a value. We don't know what it is, and we can't make any assumptions about what it is. It counts up by ones, as is familiar. And then we could do our familiar analysis with these. And also notice that the expression we get contains both n and j. And we'll have to be careful about when we use the summation identity for constants and when we use the one for loop variables, because as you'll soon see, only one of these is actually going to be considered as a loop variable. I'll keep you in suspense for just a little bit. We do that same technique of collapsing of the inner loop and saying that, or treating it like a single line that takes a variable number of steps. In the outer loop, we actually count down by ones. So we use a trick that is pretty much identical in spirit to what we've done before with reindexing and then adding some sort of offset to the loop variable or dividing it by something. We're just going to sort of count it backwards. Starting from n-1 and counting down to 0 is the same as starting at 0 and counting up to n-1, just in reverse order. And since order doesn't matter in addition, if you want to be a bit fancier, you could say addition is commutative. This doesn't affect the final sum. So even though we initially set j to n-1, and then go for as long as it's greater than or equal to 0. In our analysis, in our math, in our algebra, there are lots of different names for everything. We have our summation variable j start at 0 and count up to n minus 1. Now here's the little gotcha about variable, like different variables and whether to actually use the summation identity for variables. This is the gotcha I mentioned earlier. Notice how we separated the sum into two, one sort of grouping all the constants together, and one containing just j. We treat n as a constant because it's not the variable being iterated on. The value of n will be the exact same in every term of this summation. So it would be incorrect to use an identity that is based on a variable being changed by 1 each term of the summation. So be careful about that. We do our algebra, and we end up with the result of the constant identity here and the result of the weird, implicitly stated one variable starting from 0 identity we saw earlier. And then we account for that last loop condition check. Please make sure to do this when you're working on your assignment. And we also account for the constant time lines at the start of the algorithm. And then we get our function. One last thing that I wanted to note, or actually kind of two last things. One is that you don't need to simplify it that much more after that. Like, if you were writing this out by hand in more detail, you would probably have 1 plus 1 plus 1 at the end because you're adding 2 steps from those lines earlier in the function or in the algorithm. That you should simplify. Everyone knows what 1 plus 1 plus 1 is. But in here, stuff like n times 3n plus 4, other math courses might want you to simplify that to something n squared, but we don't need you to. In fact, it's better for the markers if you don't, because then that'll make it easier for us to see that your final function is derived from a summation that's derived from the code. And if you get it wrong, it'll be easier to diagnose what happened and give you part marks for what you did get right. Now, the real last thing to mention is that something n squared, if you fully simplified this function, you would get a polynomial of degree 2. So a polynomial where the highest power that you raise n to is 2. And I want you to sort of keep that in mind for next week. We'll say that this is a O of n squared algorithm, and that it is, in some mathematical sense, more complex than an algorithm that would run in O of n. What does that mean? You'll find out next week. That's all for today. Have a great weekend.